All right, this is our last sample of the unit. We're going to talk about escape velocity. I'm on sample 8-7 on page 354. So we've landed on a moon of Mars called Phobos. Now, we don't know the mass of this moon, but we do know the radius of it, and we know acceleration due to gravity on this moon's surface. And so we're given those two values. And so we're going to determine the escape velocity. How fast would you have to throw this baseball or anything else to have it escape from Phobos? So before we talk about the specifics of this problem, I want to show you how you can derive the formula for escape velocity, because it's not given to you on the formula sheet, and it does come up now and then on the AP Physics exam. So let's talk about Earth, or really any other planet. So for mechanical energy, bad start. Mechanical energy is equal to kinetic plus gravitational potential. We're assuming there's no springs happening here. So at the surface of Earth or any other planet, before you launch this object, we have our initial energy is initial kinetic energy plus the initial gravitational potential energy. So we can say that's 1/2 mvi squared, and that's the initial velocity, plus, and now we got to put in our less than beautiful formula for gravitational potential energy, big G, the mass of the Earth times the mass of whatever object we're tossing, divided by the radius of the Earth. That's the initial mechanical energy. Now, at any time, okay, we have the energy is equal to 1/2 mv squared, whatever that velocity is at that time, okay, minus big G, mass of the Earth, times mass of the object, divided by r. So what we have in this discussion, big R equals Earth's radius, and little r is just the distance from the center of Earth at whatever time, and I know time doesn't come into this, and we don't need the time, but at any point, right, this velocity corresponds with this distance from Earth's surface, and as this r increases, this velocity is going to decrease, right? Now, since mechanical energy is constant, we have the energy at the beginning of things, minus gm Earth, and that's a big R, because these are my initial conditions. And this is going to equal my 1/2 mv squared minus g me little m over little r. And these are my anytime conditions, right? This is a very specific velocity. This is a very specific radius. This is decreasing constantly as the object gets further from the planet's surface. So let's assume a couple of things. That when the rocket escapes, or baseball in this problem, when the object escapes, its speed is 0. Let's say we just give it enough speed to escape the gravity, right? And then also that since it can be considered infinitely far from Earth, we've escaped Earth's gravity, the gravitational potential energy is 0. That means on the right-hand side of our formula, it's all 0, right? Because our velocity is 0 and our UG is 0. So what that gives us is 1/2 mvi squared equals big G, mass of the Earth, mass of that little object, divided by r. So what I've done here, and let me just show you, is I've taken these two objects, or these two terms, and set them equal, because these two terms are both 0. Okay, so now I've got this expression here. Now I can cancel out the mass of the object that we're tossing, and we kind of thought we could do that anyways. So we get vi squared equals 2 times big G, the mass of Earth, divided by the radius of Earth. So that gives us our escape velocity equals, all under the rad, 2 times the universal gravitational constant times the mass of the planet divided by the radius of the planet. So again, if you're asked to do this on a test, and I don't think this outside the realm of possibility, you need to be able to figure that out. So maybe bookmark this sample, etc. So for Earth, if you want to take a second and chug those numbers, you get 11.2 kilometers per second for Earth. But we're not on Earth, are we? We are on Phobos. So let's start with the formula that we just derived for ourselves, the escape. And the test is going to, or the AP, powers that be, considers this just something that comes out of conservation of energy. It's not like a new thing to memorize or anything. It's just a result of this. So like I said before, I don't think it's impossible that they would ask you to do this. So let's write this, less than gorgeous fraction here. For Phobos, all right, this is all we need. We need the mass of Phobos and we need the radius of Phobos. And right now it's been a hot minute since we've looked at our data, but when we go back there, I can't seem to make that rad any longer. We learned that we don't know the mass of Phobos, do we? Okay, well, we need to take a new tact, right? What we do know about Phobos is little g, right? We're told that acceleration due to gravity on Phobos is very small, 0.00580 meters per second squared, so much less than here on Earth, which shouldn't be a surprise. Now, what else do we remember back from Unit 3? We remember that the weight of an object can be expressed a couple of different ways. One is little m times g, and one is big G, m of the object, m of the planet, or in this case a moon, over the radius of the planet squared. Okay, the mass of the object cancels out. So we can solve this. The mass of Phobos, right, and I know I wrote planet, but you get the picture, is little g times the square of the radius divided by big G. So I invite you to pause this, crunch the numbers yourself. We get a mass of Phobos 1.07 times 10 to the 16th kilograms. Okay, which ballpark should make sense, because if you flip back to the mass of the Earth, if you remember, the mass of the Earth is on the order of 10 to the 24th kilograms. So it should make sense that this is quite a bit smaller. So that gives us the mass of Phobos, and that's really all we needed to finish this problem. So the escape velocity is 2gm over r, where all of those data points relate to Phobos because that's where we are, and we get 11.3 meters per second as our escape velocity for that moon. Now going back to compare that to the escape velocity for Earth, which I just now realized the numbers are actually similar, but remember, on Earth it was 11.2 kilometers per second. On Phobos it's 11.3 meters per second. So that should all sort of make sense as far as comparison. So again, bookmark this because we'll probably come back to figuring out escape velocity. So again, here's how to find the escape velocity from any planet or moon or asteroid, and here's how to find it if you're not given the mass of a planet. I'll have to give you something else. So this was a tough question, but if you have any questions, let me know.